Math 1314, Tyler Junior College, Section 2.3, Linear Functions and Slope, General Form Part 2. You might have been wondering in the previous video why it said Part 1. Because there's going to be a Part 2. So what's that Part 2? Well, when we graphed general form in the previous video, we did it by solving for y and therefore converting it to slope-intercept form, and then extracting both the slope and the y-intercept and using that information to sketch the graph. But there's another technique for graphing, not just an equation not just an equation in general form, but any linear equation. Just think about it. Technically speaking, to graph a line, you only need 2 points. And with the exception of horizontal and vertical lines, all lines have 2 specific points, the x-intercept and the y-intercept. So we're going to discuss how to graph the equation of a line in general form by locating its intercepts. Intercepts will be a recurring theme once we escape Chapter 2. When we get into Chapter 3 and discuss other types of functions, we will always go back to how to find the x-intercept and how to find the y-intercept. The good news is the setup is always the same. However, how you find them depends upon the caliber of function that you're working with. In this case, we're just working with the linear function, so finding them will be easy. Locate the intercepts and sketch the graph of 3x minus 4y minus 20 equals 0. Wait a second, didn't we already graph this one? We did. We graphed it previously by locating the y-intercept, which I believe was at 5. And then I believe we rose 3 and ran 4 to put us at 4 comma negative 2. So just to recap what happened last time, without doing it all again, previously when we solved this for y, we got y equals 3/4 x minus 5, which put a y-intercept at negative 5, and then we rose 3 and ran 4, which put us over here at 4, negative 2. But let's pretend that for some reason that's not how we wanted to graph this line. Remember, we only need 2 points to graph a line. So we're going to locate the intercepts and sketch the graph. Now, how do you locate intercepts? Well, if you're thinking solve for y and you have the y-intercept, you would be correct. And if you were to hypothesize, if we solve for x, can we find the x-intercept? And you would actually be correct. However, you can find the intercepts much more simply, especially when functions get more complicated. To locate the intercepts, you just have to ask yourself what makes an intercept an intercept. For example, how do you get to be on the y-axis if your x is equal to 0? So, to find the y-intercept, let x equal 0 and solve. This one sentence will be repeated later on throughout the course over and over. To find the y-intercept, let x equal 0 and solve. Well, that's pretty easy because if I put a 0 here, 3 times 0 is 0, and then in terms of adding and subtracting, 0 vanishes. So you can think of substituting x as substituting x equals 0 as eliminating this x term. So if we eliminate the x term, we can cover it, and we get negative 4y minus 20 equals 0, and then we can solve that pretty quickly. Add 20 to both sides to get negative 4y equals 20, and then divide both sides by negative 4 to get y equals negative 5. Oh good, that's the same y-intercept we got before. It should be. Y-intercept is unique for a given line. Oh, but I need the x-intercept. Well, to find the y-intercept, you let x equal 0 and solve. Guess how you find the x-intercept? You shouldn't have to guess. If you're an x-intercept, you are on the x-axis, which means your y-coordinate is 0. So to find the x-intercept, it's a better blue marker than that one. To find the x-intercept, let y equal 0 and solve. And as with this first blue statement, this will show up repeatedly throughout the course, especially once we get out of Chapter 2 and into Chapter 3 and beyond. Okay, so let's let x equal 0. Let's let y equal 0. And we can use the same what I call cover and think technique. When we substitute y equals 0, the second term becomes 0, and in terms of adding and subtracting, that disappears. So if I cover up the y term, because I substituted 0 for it, I would get 3x minus 20 equals 0. Move the 20 to the other side, you get 3x equals 20. And then divide to get a fairly inconvenient 20/3. That's the worst 2 I've drawn in a long time. X equals 20/3. Now most of the time, with fractions, especially improper fractions that don't reduce or have reduced already, you would just leave it alone. There's nothing wrong with a fraction, even an improper one. I hate the word improper, it makes it sound wrong. But we're counting this off on the x-axis. So for the purpose of graphing, we might want to divide this out and figure out that it's about 6.7. It's actually 6.6 repeating, but since we're just going to estimate where it is, I think 6.7 would be sufficient. So let's locate 6.7. Let's think about this. 1, 2, 3, 4, 5, 6. This one's 6, this one's 7. It's a little bit past halfway, so we'll put it right about here. If your graph is large enough, you could actually split that into tenths and then get it a lot more accurately. And then you just connect the dots. Looks like this dot's not in the right place. This is mostly freehanded, even though I did measure the x and the y-axis. 4, -2 would actually be right about there, which is a little bit more collinear. But the point I wanted to make was we're getting the same line. That'll suffice. So the y-intercept was at 0, -5, which we had previously calculated. The x-intercept was at 20/3, 0, which we just calculated, and we got the same line. So you can graph general form either way. Calculate the 2 intercepts and connect them, or convert to slope-intercept form and then take advantage of the slope in the y-intercept. Frankly, I think the intercept approach is faster because I don't have to worry about rising and running. I just locate the 2 intercepts and connect them. I'd like to conclude this video by seeing if we can make this generic. At the end of the previous video, we generically converted general form into slope-intercept form so that we could identify what the slope and what the y-intercept were in terms of the A, the B, and the C. What you're about to see is not necessary for succeeding in a college algebra class, but it does raise your brain power a little bit. And again, for those of you going beyond this class, most likely into a calculus sequence, you constantly need to ask yourself, can I do something generically? It will make calculus easier if you can think that before you get into calculus. So how would we do this generically? Well, the same way we did it specifically. To find the y-intercept, you let x equal 0 and solve. I'm going to sound like a broken record by the end of these series, but that's how you find the y-intercept. Well, if we let x equal 0, then the first term vanishes, and that leaves us by plus c equals 0. This is pretty easy to solve. Move the c over to get by equals -c, and then divide both sides by b. And if you look at the end of the previous video, this is the same expression we had for the y-intercept. And for the x-intercept, it's the same thing. Let y equal 0 and solve. So if we substituted a 0 for the y, the middle term would vanish and we would get ax plus c equals 0. In fact, I challenge you, it's not really that difficult to just look at this equation, ax plus c equals 0, and solve it in your head. Think about the 2 moves you would do. Move the c, divide by a. The time to practice things in your head is when you're doing homework. Do not do that on tests. This is just a public service announcement. Because if you do it on a test, one of two things are happening. Number one, you're giving us less stuff to give you partial credit for if something goes wrong. And number two, you are unnecessarily risking what are probably free points to save a few seconds. That is the worst trade-off on a test. Invest the time, maximize the chance of getting your points. So as a test, I would actually I would actually hit minus c on both sides, to be honest, and then divide both sides by a. So here's the expression for the y-intercept of a line in general form, and here's the expression for the x-intercept of a line in general form. One last closing comment. Because these are fractions, there's a possibility they could be undefined if their denominators were 0. If the b were 0, this fraction would be undefined and there would be no y-intercept. But if the b were 0, I could solve for x, get that, and that's the equation of a vertical line, which most of the time doesn't have a y-intercept. And vice versa. The x-intercept would be undefined if a was 0. But if a were 0, then I would have by plus c equals 0, and I would get the equation of a horizontal line, which typically doesn't have an x-intercept. Alright, so the key thing you need to take away from this video is how to find the intercepts from general form in general. To find one intercept, you let the other letter equal 0 and solve.